As far as we know them, the laws of quantum mechanics are basic, and if the universe, they apply to the universe as a whole, then the universe has a quantum state. What is that? That's the central problem of quantum cosmology. If you don't have any state, then you don't have any predictions, because even in ordinary quantum mechanics, the probability of some alternative, like a range of position, is some projection operator multiplied, acting on the state. You take the square of it. If you don't have the state, then you don't get any predictions. So from this point of view, contemporary theories, final theories, that are supposed to apply to everything, have two parts. They have a dynamical theory, say superstring theory, and they have a theory of the quantum state. We can ask which regularities of the universe that we see, both of them are in general needed, but which regularities come mostly from one and most from the other. And I suspect here we've got an unfinished task of unification. So here's a list, a short list of properties. The Hamiltonian dynamical physics is local for the most part, at least on scales that we operate on. And so the Hamiltonian mostly explains regularities in time. The state, on the other hand, explains mostly regularities in space. And so the existence of classical space-time in a quantum mechanical universe is something we would hope would explain. The early homogeneity is revealed by this morning's speaker, the homogeneity and isotropy, the inflation, the fact that fluctuations start in their ground state, right? The arrows of time, the fact that there's a thermodynamic arrow of time, the CMB, the large-scale structure, the existence of isolated systems for which there are none in the very early universe, maybe the topology of the space-time, the number of large and small dimensions, the number of time dimensions. All these things are things we might hope are explained by the combination of these two things. Now, a theory, the combination of a theory, like a Hamiltonian and a state, predicts what we call third-person probabilities. Probabilities for which of a set of alternative histories occurs in the universe. But we don't see four-dimensional histories. What we see are making particular observations. For example, if you ask from this theory, what does it predict for the temperature of the microwave background we will observe? It doesn't predict anything, right? Because the microwave background varies with time, right? And so it will predict a history for the microwave background, but to specify probabilities for our observations, we have to specify our observational situation, in particular, in that case, the time at which we make the measurement from the Big Bang. So I've indicated that by D. In a large universe, this data D that describes our observational situation might be replicated, but all we know is there's one instance. These are called first-person probabilities, these conditional probabilities. And our objective to test the theory, we test the third-person theory by its first-person predictions, and H and psi supply some probabilistic measure on that. That means anthropic reasoning, which has been alluded to in various tones here at this talk, at this conference, is automatic in quantum cosmology if you seek to predict observations for probabilities for observations. Because the probability for an observation given data that describe the situation by Bayes' theorem is just, can be proportionally reversed. So if the probability is 0 for D, we won't observe it. So we won't observe what is where we can't exist. That's anthropic reasoning. Anthropic reasoning follows from treating observers in the universe as part of the whole thing and not somehow outside it, looking at it. Does not require a principle, it's not an option, and it's not a subjective choice.
Who's the person?
Beg pardon?
Who's the follower?
Wait a minute. Say it once more, Fernando. What was the question?
Whoever. Who's the person?
Oh, who is that? That is Everett. I wrote a undergraduate textbook in which I showed pictures of a few people, and then I got letters. I had completely the wrong pictures for other people. The whole thing had to be reset on the next. So it's possible. Now, most of our observations about the universe are of its classical history. But in quantum mechanics, a system is not sort of guaranteed or not, is not classical or not classical. It's a matter of quantum probabilities. Quantum systems behave classically when the third-person probabilities are high for histories which have correlations in time, exhibit correlations in time, governed by deterministic laws. That's true for the flight of a tennis ball when you throw it, right? Could take some orbit. For the orbit of the Earth around the Sun, in quantum mechanics, it doesn't have to be on a Keplerian orbit. It's only that in the state it's in, the probability is high for a Keplerian orbit, and equally well, it's a probabilistic matter for whether space-time behaves classically, obeying the Einstein equations. So classical spacetime is an approximation to the quantum mechanics of gravity in a given state of the whole universe. So we want to find out what the state is. Now, one thing to mention has to do with complexity. A simple, manageable, discoverable theory of the initial condition of the universe that you might write down, Stephen did, right, can't predict just one classical spacetime. Because if it did, it would have to predict all the complexity that we see in the universe, the particular arrangement of people where they sat in these chairs, and that would mean intuitively that the description of the state would be impossibly complex itself. Rather, a quantum state predicts an ensemble of possible class times with probabilities for the accidents quantum accidents that occur in them. The accidents of biological evolution over 3 billion years led to a lot of the present complexity. They're consistent with quantum mechanics, but they're not predicted with probability 1, but with lower probabilities. So the state can be simple. It only takes 45 keystrokes, I counted them, to write down the no-boundary wave function. But the individual histories can be very complex in the ensemble. As I said, an example of that is the complexity of our own universe. Another example, which we'll be talking about that's more relevant for my talk today, is the classical spacetimes of false vacuum eternal inflation. There we have a region, a space-time diagram of eternal inflation where bubbles in false vacuum, where bubbles of true vacuum are nucleated, this has been described by several speakers, giving rise to a very complex mosaic of bubbles, inflating regions, bubbles of various kinds. But we don't observe all that. We only observe the inside of one bubble, our bubble. The problem is is there a simple way to calculate what is the probability for our observations in one kind of bubble, and then we can coarse grain, that is ignore all the structure that's outside. Quantum mechanics, as I hope to tell you, supplies a manageable way to coarse grain very simply. To do that, I have to give you a 3-slide introduction to decoherent histories quantum mechanics. The most general objective in any quantum theory, as I think I've already alluded to, is the prediction of probabilities for histories. In this case, histories of the whole universe or for the Earth going around the sun. And so these are histories of space-time geometry and field. But there's an obstacle for quantum mechanics to predict histories, which you can see very clearly in the 2-slit experiment. Maybe you'd like to predict a probability for here's an electron gun, emits electron, passes through a screen with 2 slits, and makes the characteristic interference pattern over here. Maybe you'd like to predict the probability for whether it went through the upper slit and the lower slit. But in quantum mechanics, probabilities are squares of amplitudes. The probability that it went through either slit is the sum of the 2 amplitudes squared. The probability that it went through the upper slit is the sum of that amplitude squared. And the square of the sum is not equal to the sum of the squares because of quantum interference. So it's inconsistent to assign probabilities to that set of histories. So which sets of histories can be assigned? The ones for which there's no interference, right? Textbook quantum mechanics assign probabilities only to sets of histories that were measured. But we can't be dealing with that. We're not outside the universe looking at it, we're inside. And deep histories quantum mechanics, you assign probabilities to sets of histories for which there's negligible interference between the members of the set as a consequence of the theory, the Hamiltonian and psi. Like, for example, several people have asked me about Zurich, right? Like when you have an environment, particles bouncing off it in the region of the two slits that will carry away the phases between the upper slit and the lower slit. So decoherence implies consistent probabilities. We're not going to talk much about decoherence of space-time, not because there's a lack of time, but because we don't know how to do it. But I'm going to assume they decohere anyway. Whoops. Okay. Decoherence makes coarse graining easy. Let's suppose you have, this is a space-time diagram, a little too high here, x this way, t up there. Suppose we have a single particle in ordinary quantum mechanics that starts in some initial region, right, passes through a middle region, and winds up in a final region. Then the probability for that history, initial, middle, final, is, we'll denote this way, and it's the square of some amplitude which you can construct from sum over histories quantum mechanics. Suppose you're not interested in where it was in the middle. One way to calculate the probability just that it started here and wound up there is to sum these probabilities over all the probabilities for going through the middle, just a standard coarse graining. But you can do it another way. So that's this here, summing the probabilities. But it's also true that you can just sum the amplitudes over here. That would give you a complete sum over histories from I to f. And so the probability is the square of the amplitude just to get from the initial thing to the final thing. So coarse graining can be implemented that way in quantum mechanics. So there are two equivalent ways of doing it. Sum the probabilities or sum the amplitudes, effectively leaving the thing that you're ignoring out. So in quantum mechanics, coarse graining can be carried out by ignoring. Coarse graining, in this sense, enables what Hawking and Hertog call top-down reasoning in cosmology. We don't have to calculate the fine-grained evolution of the universe from the beginning all the way to the end to make probabilities for what we see today, right? We'd rather do a coarser grain calculation, putting in some data now, an initial condition, and asking how it got to be that way. That's top-down reasoning, and it's enabled by what I just described in quantum mechanics. So I now want to say how that applies to the quantum nucleation of bubbles in true vacuum in a classical false vacuum. I'm going to do this, of course, in mini superspace models, right? Easy. I'm going to assume that the geometries are homogeneous and isotropic. The geometries are closed. There's one scalar field, which is now just a function of time, consistent with the symmetries, and then it moves in a potential v of phi. The no boundary wave, the wave function is then a function of the arguments at one time, the value of A, right, at any one time, and the value of the scalar field, which I've used two different letters for to be confusing, but it also helps to distinguish them. The no boundary wave function in the semi-classical approximation is just this. It's in the semi-classical approximation, it's e to the minus a saddle point which looks like this. It's on a 4-disk. It has one boundary on which you have the arguments of the wave functions, b and psi. This thing has a radius b, and it has a value of the scalar field all over chi, and no other boundary. In general, those things are complex, but that's the answer as far as the no boundary wave function goes. I'm now going to apply that to a potential which does allow for false vacuum and eternal inflation. Here it is. This potential has one false vacuum. Here, for histories that are concentrated here, they will expand rapidly with a cosmological constant that's basically the distance up like that. But they can get out of this by tunneling through these barriers, forming bubbles of true vacuum. So a nucleation of true vacuum bubbles by quantum tunnelings, and that dominates the exit channels. There are a number of other ones. The different histories are labeled by the starting values of phi, starting here or maybe starting here and rolling down. Different slow roll regimes lead to different predictions for both for the observed CMB, which is basically a function of the form of the potential right near these minima, and different cosmological constants. I have to specify the state, of course, and it will come of no surprise that I'm going to specify Stephen's no-boundary wave function. In the semi-classical approximation, any wave function, which is a function of the three geometries and the fields, B and chi, is of this form, right, where I external is some saddle point. So a wave function in general is defined by the collection of saddle points that approximate it. If we're just going to use a semi-classical approximation, that's sufficient and really all we can do technically. So if the wave function has an integral representation, right, like we originally posited for the no-boundary wave function, it's the contour of integration that specifies the saddle points by which saddle points the contour can be deformed to pass through. The no-boundary wave function is usually specified by a Euclidean, in quotation marks, integral, by analogy with non-relativistic quantum mechanics ground states. But it doesn't have to be specified this way. In a recent paper, Thomas and his students, made it just a tiny bit by me, showed that it can also be specified by a Lorentzian one. But as in ordinary quantum mechanics, there's no reason every state has to be defined by an integral. Right? It's true for ground states, but if you take an excited state of a hydrogen atom, it's not specified by some integral, even though there's a semi-classical approximation to the orbit. And for the no-boundary wave function, the saddle points can also be specified by a dual field theory, as I helped Thomas show a little while ago. And that turns out to be an enormously powerful way of formulating the no-boundary wave function, as you will see in the next talk. The important now, several people have come up to me and asked me about Neil's talk here a little while ago. So this is my answer, right? It doesn't have to be an integral. It doesn't have to be a Lorentzian integral. We specify it by the saddle points. There is the phenomenon of eternal inflation, which Thomas will talk about in the next talk, but there isn't, I think, any of these great distinctions which are being made. Back to false vacuum eternal inflation. The theory predicts, with that potential, not one classical spacetime, but a multiverse of possible ones, with bubbles in different places, different kinds of bubbles. These are supposed to be yellow, yellow, green, and so forth. The state, these are complicated, the state has de Sitter symmetries, right? But the individual histories do not. That's important for making predictions. Because now we can coarse grain. We coarse grain over everything outside our bubble. Walls of our bubble are expanding at the speed of light. We can't see outside, right? Therefore, we can coarse grain, we want to sum over all the structure outside, which is irrelevant for us. But using quantum mechanics, we can coarse grain simply by ignoring the stuff outside and considering one bubble our bubble. So then there are only two histories, one in which the bubble nucleated somewhere. It doesn't matter where it nucleated because of de Sitter symmetry in true vacuum A, and the other where it nucleated in true vacuum B. Here are the two histories that are now involved in calculating these various coarse grain probabilities. And here's the answer. Well, we know how to calculate one bubble. The calculation was done by Coleman and DeLucia. You might worry, where are we? We're supposed to be calculating third-person probabilities, but in the usual story, there are an infinite number of Hubble volumes inside every bubble, and if there's a probability, however small, for us to exist in one of the Hubble volumes, the probability will be 1 in each kind of bubble, that there's a copy of us. So the probabilities for the C and B that we observe are just in this ratio of the Coleman dilution probabilities A and B. Problem solved. I will note that to do this measure, because we coarse grained over the large scale structure, no additional measure was necessary to deal with the infinities of the number of bubbles beyond that was supplied by the no boundary wave function, even though in a finer grain description, right, there's an incredible complexity of a very large number of bubbles. That's almost my talk, but I want to go on and make there's been a lot of discussion of multiverses here, and I want to support multiverses. By multiverse, I will mean a situation where the theory presents a multiplicity of possibilities, one of which is realized, observed, experienced, whatever you want to call it. There's already in quantum cosmology the quantum multiverse of the many different classical histories that are possible, one of which we're living in. There's the multiverse of true vacuum bubbles and false vacuum internal inflation, as I've just described, with different predictions for the cosmological constant. So quantum mechanics, by its very nature, being probabilistic, predicts multiverses in this sense. As I think was first emphasized by Bernard Carr and Martin Rees, multiverse idea is a very powerful idea because it enables entropic election, because as in this case, it enables the constants to vary. One value of the cosmological constant here, another one over here. So there's not just one history with bubbles, but an ensemble of possible histories. So it's a multiverse of histories at a given level of coarse graining. But it's much better than that, or much worse than that. There are multiverses that exist in different levels of coarse graining, as in the ones through which we calculated the Coleman dilution probabilities, which are very simple. People worry that we don't see the other bubbles. A number of things to say about that. If we have a multiverse consisting of different histories, we don't see, in some sense, the histories in the ensemble. Schrodinger's cat does not observe the dead cat, which is the alternative history, right, in Schrodinger's story. We don't see the other bubbles because they're space-length separated in us. We might see another bubble if there's a collision between them in our past. That property of multiverse is very familiar not just in physics, not just in quantum cosmology, but everywhere. For example, in biological evolution. In biological evolution, we have a multiverse of histories in which different things happened, different mutations occurred, different stuff proliferated, and so forth. We don't see it. It's in the past. We can't see it, and yet we believe it because of the evidence today. The multiverses that we're talking about here we don't see them, right? Well, we believe in them nonetheless because they're predicted by if we believe in the theory. Are multiverses falsifiable? Well, yes, they're falsifiable if the ingredients that go into its construction are falsified. Theory of the quantum state in this case, the theory of the dynamics, and that allow different vacua, a landscape, where the constants vary. Just like the theory of evolution is falsified, if the mechanisms for genetic variation can be falsified, mutation, genetic drift, recombination, and the fitness landscape, if you can get rid of that. So you can't just, a multiverse is not just some idea that's added on, independent of the theory. It's a consequence of a particular class of theories. If you want to reject it, you have to get rid of that potential, say for some reason that it doesn't exist. Well, I hope that settles multiverses. Unlikely as that's going to be, but at any rate. They're part of the theory and just occur naturally. They occur in every quantum mechanical situation. They just promoted a cosmology. I'd now like to return, since I have a few minutes, to the list I had in the beginning. I looked in my list of, I can't find my talk from Stephen's 60th birthday, I think because it used those pieces of plastic. Does anybody remember those? Right, I didn't get organized I only got organized rather late. But I did find one from the previous one, and I'd like to go over the list of the successes of the no boundary wave function relative to this list. So here's my slide. Does it predict classical Lorentzian space-time? Yes, I didn't go into the details of how it does that. It's a state. It predicts histories, Lorentzian histories. Does it predict early homogeneity, isotropy, and inflation? Yes, right? We calculate the models with those quantities, not done here, of course. Does it predict fluctuations in the ground state? Yes, because it's the analog of the ground state in non-relativistic quantum mechanics defined by this Euclidean integral, and the fluctuations start out small and they grow, just like the people that described them this morning. Does it predict the CMB? Yes, it predicts the fluctuations because it's a quantum mechanical state, and it defines what the fluctuations are and what the probabilities for them are. We can calculate. Does it predict anthropic selection? Yes, I illustrated that early on. Does it predict classical physics, after all? Yes, because it predicts that there are these histories of the universe that are correlated in time by the Einstein equation. Does it predict quantum field theory and backgrounds? Yes, at some level. You can treat the geometry quantum mechanically and keep the fields, geometry classically, keep the fields quantum mechanically, and look at those and you get quantum field theory in curved spacetime. What else have we got here? Local prediction in eternal inflation, next talk, I think. Does it predict the evolution from complexity to symmetry? How complexity arises from simplicity. The early universe is simple. It's complex now. Later on, it's going to be simple, right? When we get to the accelerating phase and nothing is left. But it, of course, because it predicts the deviations from simplicity of homogeneity and isotropy, predicts that. So that's the scorecard of the no boundary wave function. But nothing we do now compares to what we hope to do. There are many other things that might be predicted if we could manage them. The topology of space-time. After all, the topology, geometry, space-time geometry, is a metric on a manifold. So it should predict something about the manifolds. And there were very early on, there were works about how that goes. And Gary Gibbons and I wrote a paper many decades ago, right, which also gives some hints that might be true. The number of large and small dimension, why are there 4 large ones and the rest of them are curled up? A number of time dimensions, why do we only have 2? Well, it turns out that doesn't really work very well with the no boundary wave function for a reason I could describe easily, but there's not time to do it. Does it predict the unification of H and psi? Why do we have this division into a dynamical theory and a state? Well, we don't have that, right? So that's still something I think has to be done. Populating landscapes, hints, and finally there's quantum mechanics itself. What evidence do we have that quantum mechanics, which has been tested only on very small scales of the laboratory, right, and maybe in the beginning of the universe, if you believe these stories, applies to the universe as a whole? It's a little bit strange, right, to have a theory which involves the principle of superposition when there's only one state in the entire universe. Is there something deeper from which quantum mechanics emerges? Well, we don't know. So, Stephen, happy birthday, right? There is still a lot to do. Thank you.
Thank you very much. So there are probably some questions. Yes. You wait for the microphone.
Yeah, I'd like to ask about the, you seem to have implied that the no-boundary proposal is relatively unique, but certainly otherwise in quantum mechanics we're usually faced with an enormous number of possible choices of states. And among your list of predictions, wouldn't many of those also come out of other distinct choices of vacuum states? For
Probably.
example, Vilenkin's
We don't have any,
tunneling.
yeah, we don't have any evidence that's unique. I can tell you the history from my point of view. So any solution of the appropriate Wheeler-DeWitt constraints is a candidate for the wave function of the universe. So there's certainly plenty of them, right? Long ago, right, we were struck by the fact that the observational evidence shows that the universe, then at the time, was simpler than it is now. More homogeneous, more isotropic, more nearly in thermal equilibrium. Those seem to be properties that are associated with the ground state. But there isn't any ground state in the cosmology, closed cosmology gravity, because the Hamiltonian is zero because of time reparameterization invariant. But in non-relativistic quantum mechanics, you don't have to calculate the ground state from h psi equals E psi. You can calculate it from a Euclidean integral. So the idea was maybe the Euclidean integral will give us a state. And it's true. It gave us a state, right, for which I've just listed all the successful predictions. For example, the fluctuations starting on the ground state, that was something that would naturally occur that was the analog of the ground state. But I can't exclude that there couldn't be other ones, right? We really think of the no boundary state as a kind of model, right, for if we have a deeper association, for example, as will be described in the next talk, with dualities, we might learn something different.
More questions? Yes.
That's it? Where are we?
So is there any way you can make any sense of the idea of a pure state in terms of what we could observe?
Sorry, is there any way we can?
A pure state for the, in other words, we can't observe the whole universe, right?
No, I don't think so.
And so there's no sense in which you could ever test whether the universe was in a pure state.
No, so that's an assumption.
It's an assumption.
Yeah, so because I think every system does have a state, despite what a lot of people tell me, right? So it's the sort of simplest quantum mechanics we can do. I don't think you can test a pure state, not unless you can replicate it, right, and then do it all over again. Right? Bad luck for that. But maybe there's something, it seems to me you're losing information despite, I understand the standard objections to this point of view, but I believe mine anyway.
Yes.
So on your checklist, you had one entry locality which didn't have a score. So could you please elaborate a little?
It was probably keynote incompetence or something. A locality. Why are our field theories local? It didn't have a score because I have no idea why it should be local. Is it anthropic? That is, we of course exploit the locality all the time. You went to lunch up there, right? You came down and sat down here, you're functioning fine. And indeed, it'd be hard to imagine IGUSs, or rather information gathering utilizing systems. They exploit the locality because they learn here, apply there, right? And they move in between them. But is that just our particular situation? The trouble is we don't have any idea, except this is the realm of Fred Hoyle. Do you remember, you're too young to remember the black cloud, remember the big object that came around the sun and was intelligent? We don't have any idea, but all the ones we've seen so far, which are very limited, exploit locality. Oh, so why is that? Is there some other reason that the theories are local? Why aren't they non-local? That's why there's nothing in the box.
Yes.
It didn't answer that question. It assumed it. Yeah.
What are the prospects, if any, of testing any of these things with analog condensed matter systems, for example?
Well, the analogs in simple systems are the ground states, right? So there's plenty of opportunity, but the fact that ground states can be computed in certain ways, I wouldn't say the success of that project. High symmetries, for example, is a characterization of condensed matter ground states, typically. I wouldn't build much confidence in a theory of the universe from the success of those theories in the laboratory. The context is so completely different, having a universe in which we're inside, not measuring, just experiencing, and differing from a laboratory situation where we measure, control, and it's all out there.
Okay, thanks very much. Let's thank Jim again.